Hello everyone. In the previous part, I discussed the fundamentals of neutron activation analysis technique, very powerful technique for determination of concentration of elements. And nearly 70% of the elements in the periodic table are amenable to neutron activation analysis. Different elements have different sensitivity, different detection limits because of their nuclear data. In this part, I will discuss some of the applications of neutron activation analysis. So, neutron activation analysis has found applications in large variety of fields, starting from geology to biology, food and nutrition, environmental sciences, nuclear technology, chemical sciences, even in healthcare, archaeology, forensic sciences, and material sciences. So you can see wherever in any area where it is required to find out the concentration of elements, you will find neutron activation analysis is one of the important techniques worth considering. And particularly in those areas like nuclear forensic science, archaeology, or even the geology, where you may like to retain the samples for any future investigation, then this technique scores over other techniques. If the idea is only to determine concentration, there may be techniques, like chemical science, material science. You may have other techniques like spectroscopic based techniques. But those samples which are mixed samples, and you may have, you want to preserve the sample, but you are looking for a particular element, then you will find if that element happens to be sensitive to neutron analysis. And so people working in different fields have taken NAA for their studies in R&D areas. So I will not be able to cover all of them. I will cover some of them like archaeology, forensic science, geology, food and nutrition, and healthcare. So let me see how much justice I can do with this. Okay. So archaeology, there are excavations to know the past civilization. But there are many areas where archaeologists want to find out what is the composition of a particular artifact which is found out in some excavations. So, or for example, like I was telling you that you can do dating of the fossils. So archaeologists would like to know how old a particular place is. For example, there is a temple and you want to find out when this temple was built. You just take a fossil sample, the wood sample from that, and you can find out the age of that temple. Similarly, you have then the ancient pottery samples. So from, like, for example, Mohenjo-daro and Harappa, you get some pottery and you want to know the concentration, you want to understand the kind of technology people had at that time. And nowadays, somebody may claim that this is of that origin. So it is Harappan time. How do you make sure this is of Harappan time? It is not a fake. These days, there is a lot of adulteration in many things. So even suppose somebody is selling a archaeological artifact and earning money, one would like to know scientifically whether it is of that time. So you need to characterize that artifact. You need to find out what is the origin of this. So the ancient pottery, they had well characterized concentration of different elements. There is a signature concentrations of elements. So you can do analysis of this pottery and find out that this is genuine or not. Obsidian, a type of igneous rocks. So you can try to understand the volcanic eruptions that happened, what kind of rocks were generated in the volcanic eruption. The shards, this is the sedimentary rocks, how the sedimentation process took place, over a period of time. The basalt and the limestone type of the clays, different geological and archaeological samples, so you can analyze as a data of research and development, or to characterize and do some origins of these artifacts. So this is a particular gamma spectrum of an ancient pottery sample. A sample was irradiated for, let us say, 5 seconds the TI irradiation 5 seconds. After the irradiation, they waited for 25 minutes to cool the sample. Cooling means e raised to minus t, lambda Tc. So cooling may be required because it makes some time to take the sample out of the reactor to your laboratory. That may take some time, and sometimes you may produce some shorter-lived activity which you have not of your interest. And then it was counted for 12 minutes. So I have taken this from the reference of Michael Glasscock. And you can see here the interesting aspect of this is the typical gamma spectrum of a HPG detector. You have up to 3 MeV, 3000 keV. So you can see a large number of elements the isotope have amenable to gamma ray: dysprosium, barium, titanium, manganese, magnesium, sodium, aluminum, vanadium, potassium, all elements. So sodium and calcium. Sometimes one isotope may have several gamma rays like sodium. So like that, in one shot, one spectrum you can analyze. You can see 1, 2, 3, 4, 5, 6, 7, 8, 9, about 8 to 10. Sometimes even it can be more. So a single gamma spectrum, one counting of the sample, you can analyze multiple elements in the sample. So that is the beauty of this, and the archaeological samples of very varied sources can be analyzed to find out the source of the particular artifact, or you can even do research, how the evolution took place, you can understand by neutron activation analysis. Another classes of this, like sometimes you can do the provenance study of archaeological samples. Again, this is the kind of pottery, large size potteries. There was some, sometimes when you are doing research, archaeologists may like to do some investigation of ancient potteries and to establish their source, where from they came. And so for such samples, in fact, in my department, one of our colleagues, is an expert in the neutron activation analysis. So he has supplied me this data, Dr. Acharya. So he has used these samples, and these samples, now you can take a small sample of this artifact and do the neutron activation analysis. And as I mentioned, that in these samples, it is not known what are the elements. We cannot have the standards for this. Reference materials are not available. So at that time, the internal mono standard. That means this sample one of the elements in the sample may be used as a reference isotope, like scandium. So scandium has got decay characteristics. We can use them. So all elements with respect to scandium, we can determine their concentration. So scandium has good geochemical properties and nuclear properties, the decay characteristics, and scandium is in the family of rare earths. So scandium, yttrium, and then below is the lanthanides coming. So chemically, they are similar to lanthanides. So this is a typical efficiency graph, because what you require is a good efficiency data. Relative efficiency of detection depends upon the gamma ray energy. And so the uncertainties are introduced, because suppose you have this scandium gamma 1 here, and you are using the other gamma here, so ratio of efficiencies becomes important. If you do not have a good efficiency data, then your analysis may be wrong. So in situ relative efficiency of the pottery from the same sample, you generate the efficiency data, because the standard is also in the same sample, like scandium. And so you require to have the gamma rays, multiple gamma rays in the same sample, and internally you can generate the efficiency data with respect to that standard, like scandium. You can determine the concentration of all other elements. And so you can now do the provenance study. You can generate the data of the concentration of certain group of elements which will characterize the particular pottery. And then this is the kind of study you can do. You do not need any external standards, because initially you don't know what are the elements present in that. So this is the kind of research one can do to characterize the samples of ancient origin in archaeology. Another is the geology, earth, and apart from earthly objects, you can do the meteorites that are coming from the planets. So these meteorites, these meteors that are coming to earth, and you would like to know from which planet, or from there it has come from some other place. What is the source of this meteorite? So the geology people, they are trying to characterize the different meteorites present, and you can even compare with other meteorites. So one of the studies was analysis of meteorites by internal monostandard prompt to gamma neutron activation analysis. Suppose you have a big chunk of meteorite. So in prompt to gamma, as I mentioned, the neutron beam is out of the reactor building, reactor hall, and then you can expose the entire sample to the neutrons, and then the gamma rays are detected by the detector. So in Odisha, in September 27, 2003, a meteorite was fell on the earth, and that is named as Jagannath meteorite. So this Jagannath meteorite was characterized by colleagues at ARC, and it is published in journal. I have taken the data from Dr. Acharya, and you can see here the elements that are present: iron, silicon, chromium, potassium, magnesium, calcium, nickel. Jagannath meteorite concentrations you can see in terms of the percentage. All of them are in percentage: 27%, 15.1, 0.39, 0.18, 11.6, and so on. And you can also compare them with other meteorites elsewhere published by other colleagues, other researchers, Kobe meteorites, Czech meteorites, and then you can do whether it is whether it is an authentic meteorite, or what is the origin of this, whether it is different from this meteorite. So what was found that the elemental concentration of this meteorite was found to be different from that of the Earth's crust, and it was found to be close to these other meteorites. So essentially, they wanted to confirm, first of all, that it is an authentic meteorite. It is not, no, somebody may say, it takes a rock and say, this is the meteorite. So sometimes people may do business also. They just sell this meteorite, it is from other planet. So to make sure that it is an authentic meteorite, and also to compare it with other meteorites, and you can do R&D. So what are the source of these meteorites? So this kind of study one can do in the field of earth and planetary sciences. Then one of the most important area wherein the neutron activation finds a lot of applications. So I'll just do one of a story from, not a story, the actual research that happened in the case of investigating the death of Napoleon Bonaparte. Napoleon Bonaparte was the French dictator in the 19th century, and he was actually defeated in the War of Waterloo by the British Army in 1815, and then he was exiled to a place called St. Helena, and there in exile Napoleon died. So there were a lot of speculations about how Napoleon died, whether he was poisoned or not. And so you see, 1850-21 is a long time past, but still, when he was a emperor, and so some scientists wanted to investigate that he died of poisoning or he died on a natural death, because he was not very old at that time. So then in 1952, the hair sample of Napoleon were collected from that place, St. Helena, and this hair sample was subjected to neutron activation analysis by neutron capture reaction on arsenic 75. Arsenic is monoisotopic, so you get arsenic 76 by N-gamma reaction. And what was found that the activity of arsenic 76 in this Napoleon's hair sample was found to be 7 to 38 times higher than what you get in the normal hair. So it was no doubt that Napoleon's hair had very high concentration of arsenic than in the normal. Okay. The question was whether Napoleon was poisoned with arsenic or not. In 1987, this investigation was going on. They wanted to investigate where from the arsenic came into the hair. And so they found that there was a wallpaper in Napoleon's house in St. Helena, and the pigment in that wallpaper was some pigment which contained arsenic. And arsenic is known to form volatile compounds. So the green pigment contains arsenic, and it is possible that under the conditions, atmospheric environmental conditions, arsenic might get airborne. And the arsenic is known to form complex with organic molecules, and then it could be inhaled by Elena and this Napoleon, and might have killed. So there was a theory going on in that time that Napoleon was poisoned slowly by giving him arsenic laden food, but it was not known who killed Napoleon. And of course, what was the motivation for killing Napoleon, because he was already in exile. But it generated a lot of interest among the community historians. They wanted to know what is the by Napoleon, whether it was he was really poisoned by arsenic. We don't know. But a lot of research went, and the neutron activation played an important role in coming to this conclusion that Napoleon's hair contained large concentration of arsenic than what is present in normal people. You can see here, this is the gamma spectrum of arsenic 76, 559, and 657 keV gamma ray. So you can selectively you can find out peak area of these peaks and find out the concentration of the arsenic in the sun. Another area in the forensic science where neutron activation analysis is used in the gunshot residue analysis. In the crime investigations, somebody fires a bullet and the gun is recovered from the site, but then you want to know who fired that bullet. So the culprit, you have to unambiguously prove. So see, in many places, you go by the witness. The witness says, I have seen this person firing, but the witness may turn hostile after some time. So the statement of a witness, it can vary, and you cannot rely on the witnesses for the final judgment. So always, forensic science relies on the scientific evidence of the culprit. So you have to correlate with the weapon and the culprit. So how do you do that? What was found that this gunshot residue, if somebody fires a gun, then that person's hand contains the residue of the gunpowder. So you can analyze the gunpowder from the hands of the culprit. Of course, by the time if the culprit has washed the hands, then you cannot do anything. But if you can catch the culprit and you can get some sample from that hand of the culprit, so the alleged culprit, analyze that samples for the particular component. So in this case, barium and antimony are the two elements which are not very common in the soil samples or dust samples. At our, suppose you get some dust, so it may also contain. So these are not very commonly available. Like commonly you get iron, scandium, aluminum, and so on, manganese, magnesium, and so on. So what was found that this gunshot, gunpowder and gunshot residue contained barium and antimony, and they were actually taken as signatures of the bullets that are the gunpowder that's used. And so if a person's hand was found to be contaminated with these elements, he is a prospective culprit. So gunshot residues, GSR, to be abbreviated, left with the hand of the individual after firing can be used as a scientific evidence for correlating with the person who did the crime. The barium and antimony are present in these residues. And so what essentially do the different types of the guns, you can collect the data, the kind of concentration ratios of barium and strontium from in the guns of different types of firing guns and the different individuals, and you can generate a database, and then you can pinpoint that suppose you recover the gun that was from the crime scene, and you have 10 people who are suspects. So you can analyze the sample from the persons and correlate. This is the person whose sample is matching with the gun recovered from the site. So that is the kind of scientific evidence generated. Maybe scientifically you can nail the culprit. Then one cannot escape. They have to accept. This is the kind of analysis people do in the forensic investigations. Then in food and nutrition, there are lot of applications. And people who are doing research in this area, you will find NAA is very, very popular. So there are many elements which at trace level play a vital role in our biochemical system, enzymatic processes. There are actually like they are micronutrients in the. There are many elements which are beneficial to our health, and those elements, see, there is a deficiency of these elements, we get sick. If there is excess of this element, then they become toxic, and there is an optimum level of concentration of these elements they are required for a good health. So the deficiency or excess of certain elements in our body leads to disorders and diseases, and therefore, we need to have a balanced diet, very controlled diet containing those elements. Certain elements are toxic; they are not needed by our body, like arsenic, mercury, chromium, lead. And out of them, certain elements like selenium. In fact, arsenic has got medicinal value. Some of the, some people used to recommend this mercury laden asthmas, also contains, they have some medicinal value. So, but in terms of the nutritional elements, selenium and iodine are nutritional elements, they are required for the body. For example, selenium, actually, I will discuss more on the selenium NAA. Selenium, this is present in organoselenium, is useful for the body. And the selenium can also lead to abnormalities in the humans and animals. So it is essential for the body at low concentration, but at high concentration, it becomes toxic. So we will discuss the NAA of arsenic, selenium, and iodine. In arsenic and selenium, there are no limits prescribed by the WHO, World Health Organization, that any drinking water should not contain arsenic or selenium less more than this concentration, like 10 ppb. So, and then since these elements are useful for our body, we require them. There are recommended daily intake values. For example, for iodine, we have 50 to 150 microgram per day. For selenium, people have been taking this kind of concentrations. And so these are the elements, either if they are in deficiency in our body, they can lead to problem. If there is an excess, they become toxic. They can lead to even like thyroid disorders are due to iodine problem. So all the three elements are amenable to neutron analysis. Arsenic 75 N gamma, iodine 127 N gamma, selenium 76 N gamma. So they are, I will give you some examples of activation analysis using for these elements. So arsenic in environment, there are safe limits for drinking water, less than 10 microgram per liter, ppb. So it has the good and the bad part of it. Arsenic in trivalent state has shown remarkable arsenic oxide, not trivalent, not arsenious acid, but arsenic oxide. Arsenious oxide has found to be therapeutic efficacy. Patients which are suffering from acute prophylactic leukemia, and methylated arsenic, organic arsenic, has been known to have anti-cancer activity. The bad part of it is that arsenic can induce carcinogenicity in the human beings, and there are many areas in the world, including some part in our country, they have about more than 40 countries in the world have drinking water concentrations more than 10 microgram per liter, and that leads to arsenic toxicity. Excess of high concentration of arsenic affects organs, causing to dysfunction of many organs, damaging the organs, and so. So arsenic, can become airborne because it has a tendency to bind with the organic molecules present in drinking water and food. So many, people are susceptible to arsenic poisoning. As a species, arsenic is present. If it is arsenic acid, arsenic is in pentavalent state, it is less toxic than arsenious acid, which is in the trivalent. So trivalent arsenic is absorbed by the body, and it can lead to hydroxy. Organic arsenides, they are considered to be less toxic, and so some of them in fact have some medicine for therapeutic applications they are being utilized. As I was telling now, the oxidation state of arsenic is important. The trivalent arsenious acid is more toxic than pentavalent acid. And so people are doing the speciation. That means you separate the elements depending upon their oxidation state. And for inorganic arsenic, one can use a cation exchanger, anion exchanger, Dovx 1x8 in acetate form. So one of the columns will retain arsenic 5 and elute arsenic 3. And then the retained arsenic 5 can be eluted by some other. So a lot of people who do research in food and nutrition, they need to also separate arsenic in different oxidation state. So this is one of the study of our colleagues at the BARC. They found that you can separate more than 95% of arsenic with a good radiochemical yield using ion exchange and sound extraction. So speciation in neutron analysis in combination with speciation becomes a very important tool to study the toxicity associated with different oxidation states of element. Iodine is another important element which is required for the body. Our body, like thyroid hormones, contain iodine. Like there are 3 thyroid hormones, T3, T4, and TSH. And what is the source of iodine that we have? It is important to know the content of iodine in different food samples. So we have milk powders. So this group did actually the nutritional analysis of different milk powders, baby food, different baby foods, low fat milk powder, and so on, and found out the concentration of iodine in milligram per kg, and the gamma ray spectrum of iodine, 127 iodine, and gamma 128 iodine. You can see the 443 keV gamma ray, highly selective. So you do not have any doubt there is no interference in that peak area. So this is the kind of study people do to find out iodine in different. So you can just irradiate the powder without doing any chemistry. Irradiate, seal it in a container aluminum foil, irradiate and count for gamma activity. You can find out the iodine content. Selenium is another important element. It has got both the aspect good and the bad. Low selenium content, there can be selenium deficiency. Selenium is required for our body. Selenium deficiency can lead to diseases. For example, there is a skin disease called keratosis pilaris. It leads to cracking of the skin. Skin becomes very rough because of the selenium deficiency. Excess of selenium in our body leads to, along in animals, cracking of their hooves, and cracking of the nails can take place if we have excess of selenium. So normal range of selenium. So selenium can be picked up by different plants, and when we consume those plants, our body will accumulate selenium. So in soil, selenium content is an important parameter. If there is a selenium rich soil, then the people living in that area, people eating the vegetation in that area, are prone to getting selenium problems. So normal concentration is 0.03 to 0.08 microgram per gram ppb, and selenium concentration can go to very high. In fact, very, very high concentrations are also seen in the world. So while selenium in excess concentration is toxic, and low concentration is also not desirable, and low concentration, the deficiency of selenium can lead to diseases. There are the good part of selenium because it is essential to health. Selenoproteins are required for generating thyroid hormone T3 from T4. So to convert T4 to T3 requires selenoproteins, and selenium is believed to play important role in the brain development. So you will find that it is again this story where an element is good for health, at the same time, when there is a deficiency or an excess, then it can lead to disease. So these are the results of a selenium determination by neutron analysis, and you can see mustard, a particular mustard from the particular area was found to contain very high concentration of selenium. So people who are consuming that mustard might be getting excess of, and this also shows that selenium can be localized. Particularly, the mustard contains some sulfur compound, and wherever there is sulfur and selenium are homologs of each other. So selenium will go along with sulfur. So any plant containing excess of sulfur will enrich the selenium. Therefore, it is important to study the concentration of selenium in different plants so that one can understand whether there is a selenium related diseases in the population in the area. So lastly, these are the another area of study was this coal fly ash. There are thermal power stations emitting a lot of flue gases, and these flue gases cause pollution in the area around the thermal power plant. You will find a lot of dust settled everywhere, and there are the people who are exposed to this the dust, they get diseases. So it is important to convince ourselves that people living in that area are safe. So that dust, the coal fly ash, was analyzed in our laboratory for the concentration of this metals. You can see sodium, magnesium, aluminum, potassium, scandium. So whatever is percentage, rest are in ppm values. And you can see here different samples, the concentrations of the different hundreds of ppm, strontium, cerium, niobium, thorium, and uranium. So this coal fly ash can be used as a rich source of certain elements, whereas at the same time, high concentration of certain elements can lead to diseases in the area. And so, in the environmental clearances of certain plants, these are the data utilized for seeing that the plant is working in the proper way. So that's all I had to convey. There are many more applications of NAA, but in the short span of time, one you can always go and look literature and see what are the kind of different applications in different area. So I'll stop here, and the next lecture I will take the ion beam analysis under nuclear analytical technique. Thank you very much.